job, Art.
This is yours. Thank you.
Good job. Hey. So this is an A, right?
Yeah.
All right. And then it should be this one. I'm sorry.
You're good. Thank you.
I was got the two options. I messed up. Sorry about that.
That's fun.
All right, so the one we just take a look, it's on page, on part B, question number 2. Cody just showed it to me that I messed up. I was supposed to write the coding in the template strand, and it was supposed to be 5 to 3 prime and 5 to 3 prime, but I forgot to flip the numbers. You can see it says 5 prime and 5 prime on both sides. So it means technically I wrote them in wrong, right? So it's like, I saw some people translated that word using they flipped the template strand back and made the protein out of it, right? So that's my mistake on me. So right now, I just caught it right now, so I might have been taking off points for that question. If I did, I tried taking pictures of it. I'll try to update them on my side. So hopefully by Monday, your grades reflect the midterm. Like it should be bumped up for that reason. If not, come talk to me to fix it for you. Yeah, that was on me. Any questions on the midterm? Any stuff you guys want to go over? Good. All right. So let's get started with today's stuff. Oh no. So I was looking at my little clicker response thing that we did last week. Again, I made another silly question. That was like, you want to use the technology or the other thing? The answer was yes or no. So everyone said yes. Someone said yes, you want to answer questions. So I like that. I'll re-put that survey up there, and then I'll make it I'll make it correct this time. And then the questions that I got for it were also they were really good. I think they were basically trying to get me to talk more about the energy itself, right? And the kind of the pumps. So I'm gonna do a little bit more drawings that I'm gonna add kind of into this PowerPoint that'll help answer those questions. If not, we're gonna write them. I wasn't able to make the survey for today, but we'll write them on here and then I'll go over them next time. What happened?
Thank you.
Here, down. So that should get to my good here. And then double check part B. Question 3, I kind of messed up. Good. All right, so we're going to be talking right now about basically how we're going to be using chemical reactions. And we're going to be kind of trying to keep track, not of the molecules themselves per se, but more of the energy that they currently have and into the energy state that they end up with after the chemical reaction. And the biggest one we're going to talk a lot about today is going to be ATP. So for this, we can use this little drawing. All right, so ATP is going to be the big player that we're going to talk about a lot. So here we're looking at basically your delta G or your free energy, right? So how much energy the system has to do work. When we're talking about ATP, I want you to be thinking of this one as it's a molecule that has a lot of potential to do work, right? So we're going to be thinking about it. I want you to think about energy-wise. It itself has a lot of energy. as a molecule, right? This molecule can then get broken down, and what we're gonna end up having is we're gonna creating ADP. Right. So we're gonna go from a triphosphate to a diphosphate. And remember those phosphate groups, it's a P with 4 oxygens around it, which is a big, big negative charge, right? And then what we kind of measure is you're basically looking at what's happening when it's when you're going from this, which let's say this is our reagent. So this would be our reagent side, no reactant. And this is your product. So we're going from ATP to ADP. When you go from this to this, you're breaking this up. You're gonna have ADP, plus you're also gonna have an extra inorganic phosphate group, which would be 1P with the 4 oxygens around it, right? Going from here to here, what you're gonna have is you're gonna have a big drop in energy, right? So basically, this is the energy that you have that kind of leaves this system when this reaction breaks open, yeah? So then, when this is going from a high energy state to a low energy state, I want you guys to be thinking about kind of like last week, the guy who's on top of the diving board, he has a lot of potential energy, that would be your ATP. And when he jumps off, him moving to that, getting all that kinetic energy, that's what he's releasing till he gets to the bottom of the lake, right? So here you have a lot of basically energy stored up in the molecule that you can release. So then this part here, for ATP, they've actually measured it. And this is gonna be, when you write your delta G, it's gonna be a negative 7.3 kcal per mole. The big emphasis here is gonna be that it's negative, right? Negative meaning that when this reaction happens, it actually releases energy. So you initially have energy stored up, it kind of goes away as you proceed forward, right? Because it's negative, it also gives you the idea that it's gonna be, you're gonna be able to label this as exergenic, right? That means that energy is coming out, so this is gonna be being released into the system. The other thing is it's gonna be spontaneous. Yeah, spontaneous, yeah. Now, we can talk a little bit about something that's kind of opposite to that. And which is the one I have from here. Yeah. The opposite to that one, I want you guys to be thinking about is if we did the same drawing like this, and then the goal was we're going from, there would be glucose and fructose, right? GNF, which is these 2 different sugar molecules. They're basically at a low energy state, like they don't have that much energy per se. If you glue them together to become one bigger sugar molecule, you're basically making a molecule with a higher energy, right? So it means you're going from a low energy system and you're trying to bring it up to a higher energy system. In order to make this jump happen, you need to actually put something into that system to make sure it goes up, right? So basically, this change in height, this means energy has to go in, right? Make it go from here to here. And again, we're still looking at what's the energy in the system, right? All right, so we have this jump going from these 2 independent sugars, and you're making them, linking them up, and you make a sugar, right? If we look at the value of this, in this case, your delta G is going to equal a positive number, right? Kcal. So, I didn't write this number down, but let's just put a temporary one, just a placeholder. Let's say it's 5, right? Just put the folder for a spot. It's not the real number, but I just need something positive, right? The difference is we're going from this low energy state to the high energy state. You need the energy to go in to help power this reaction up. And this is Endor. Genic. And then this is not spontaneous. Because you need to power that reaction to make it go forward, right? You need to put work into it. this kind of making sense? You guys really comfortable so far? Yeah, about you can jump from one state to the other one? Fine. Question? Good. How do we do with this? All right. Two different states, right? High energy to low energy to high energy. Yeah, all right, cool. Now, if you guys feel comfortable with that, we can start. All right, so let's talk about how this work's gonna happen. So here, the one that we use a lot, or the cells use a lot to work, is they basically use ATP. Right? So in this case, the cells put in the work on making this chemical, ATP. The moment you have this being made, you can take advantage. Now, wherever you move this small molecule to, right, you can have this reaction happen, and you're going to release a lot of energy from it, right? So you can use it to help power up other things. In this kind of work, there's 3 different types of work that the cell can do. One of them is going to be like this, which is chemical work, making and breaking bonds, right? The other part is we can use the ATP itself to help do transport. Like remember last week we were talking about those little pumps that we form to help move a molecule against its gradient. That's the ATP giving energy to change change the shape of the proteins to help move the molecules. And the other one is you can also use it for mechanical work. And this could be your actin and your myosin. When you're moving those motor proteins, they're going to be using ATP to kind of power them up. All right. So we're going to get a lot into talking about this chemical work and how we actually can couple the energy to make this happen. So for this one, we're going to dive in super into ATP itself, what it's shaped like. So this is ATP, kind of like what we're talking about for the DNA, right? You have your base, you have your sugar, and here's the very important part. You have your 3 phosphates with oxygen. They have a huge negative charge. Yeah. Because there's a big negative charge in this region, these molecules are next to each other. I almost want you to imagine like they're kind of, those oxygens are shoving each other. So now you have this thing that has a lot of energy and there's a lot of motion and they're kind of pushing at each other, making it even more unstable. Keep that bond. Right? So you can imagine that this covalent bond, this covalent bond, are trying to push it together. At the same time, these 2 negative charges are trying to push each other away. These 2 negative charges are trying to push each other away. So, maybe like if you're trying to hold hands with somebody, at the same time you're kind of pushing your face and your body, right? You're playing soccer.
I play lacrosse.
You guys into sticks, right?
Yeah.
Yeah. See, that kind of helps keep the other player away. So that's the unstable state of like, you know, they're not going to be around you that much because they get smacked. Right? Yeah. It helps them a little bit. These molecules are doing the exact same thing. So our cell's going to invest its work putting this thing together. Now you have this thing of like these 3 long phosphorus walking around hitting each other with sticks, which is like wherever it goes is going to be high energy unstable. And they're basically going to power whatever we need to power up. All right. So here we're doing actually the drawing that's explaining this, right? So on this side, we're saying we have high energy. You have this molecule, right? So that's going to be our reactant. This is what's going to set it off. This is going to get water to come in. You're going to do hydrolysis, right, which breaks the molecules apart. Here, you're going to kick out one of those phosphate groups with all the oxygens. You're going to release a lot of energy, and you're going to end up with ADP. So in this drawing that I did here, I got a little bit lazy. In here, you can put ADP, phosphate, and there's your energy coming out, right? That's the actual measurement of the energy that's going to come from this. All right, so for this should have been my clicker question. So on your little note card on the top or something, put is it endogenic or is it exergenic? Just put number 1 and then answer this. I'll give it away. Never mind. All right. So now here on the left, we're still looking at that ATP releasing, going from the side energy state to low energy state. That means that when it's doing that, it's dumping out energy, right? This energy that it's dumping out, it can be transferred from one chemical reaction to another one. And this is what's called energy coupling. And then what you can do is, you're like a reaction on the right, which is endogenic. And it requires energy to go from a low energy state, time to charge it up. You need to bring the energy from this ATP, you can transfer it to this molecule, right? So again, going back to our example, let's say the reaction was Let me do it for this one. Yeah. Here we're looking at this sugar reaction, right? We want to glue these two sugar molecules together to make sucrose. So we're going from a low energy state to something being glued together to a higher energy state, right? It doesn't want to do it by itself because it needs energy from the environment, and that's when the ATP comes in. What's going to happen is the first steps, your triphosphate is going to transfer one of those phosphate groups. So it'll be in a high energy state here. It's going to give the charge to the glucose molecule, right? So in that intermediate step, if you imagine before, kind of like in my drawings, glucose was down here. It's a low charge particle, right? The moment you add the phosphate to it, what's going to happen is you're going to temporarily charge it up. And now the charge of that glucose plus the phosphate, so imagine we do a little extra charge, it would be something like this. This is your glucose plus the phosphate group you added to it. So technically, the charge of the ATP is higher than this yellow version, right? So it means that now this is still going to be able to produce forward because you're still able to transfer energy and you have enough to make it undo from here to glue to this. Now, the cool thing about that now is that you look at this glucose and this phosphate, now they're charged up, right? So they're the high charge particle that's unstable and it's more charged than the final product, right? So it's basically trying to go into that disorder state. When it does this high charge particle, it's like lower down on the energy scale if it moves in with the fructose now, right? So now that it was low charge, you charge it up with the phosphate group, it's easier for it to kind of like fall down or like it goes into its lower energy state when it moves into the sucrose. Yeah. So you can see that I can use the energy from this, power up the glucose, and now the reaction is technically moving down. If you look at the area under kind of like the little triangles that we're drawing, see, you're still going to be able to release energy. So you went from having an endogenic reaction of trying to glue these two things. By using the phosphate, you've technically set up an exergenic reaction, right? That glucose is high charge and it's kind of crashing down into this low charge state. Does that make sense? Yeah? No? If not, I found a super awesome interpretation of this. So here we're going to be looking at two reactions, right? So exergenic means you let energy out. Last week's example, that was a guy on a diving board jumping off. High energy, and he's going to a low energy state, right? So here, the people on top of this diving board, there are high energy particle that's going to release energy. And then the person at the bottom of this little inflatable thing, he's the low energy particle, right? And they're going to be able to release their kinetic energy into the thing. Oh, let's watch it, you'll see. I'm gonna mute it because they were yelling some stuff, but look at this. So there's multiple of them on top. You have that extra ATP. Boom, you transfer it, and now that becomes the high energy particle, and it, right? So if we look at, kind of do an analogy from there to there, this was the group of people on top of that, on top of the platform, right? They have all the energy. When they jump in and they do that kinetic energy transfer, they charge up that glucose. Now it becomes the high energy particle, and then it can do its thing between that high and crash into the next molecule stand. That make sense? Yeah? All right, cool. Yeah, I'm gonna hide it because the people in my teaching the class have the same PowerPoint. They're gonna not know what to say there. All right. So does that kind of make sense? How you can use basically a reaction that wants to go forward, and you can use its energy to power a reaction to go against its gradient, like in the direction it doesn't want to go. Yeah. Midterm question. Final question. Yeah, I'm gonna make my final tough. I wanna fight you guys.
No, we need to end well.
Always end with A's. I mean, I can push it. You guys are good. All right. The next part, so ATP, like I said, it can fight. You have a lot of energy. It moves stuff around. You can use that energy in chemical bonds. The other two types, which I'm not going to talk about that much, is going to be for transportation and for mechanical work. Right? For this case, when we're looking at transport, here we're going back to what we talked about the membranes and how you can move molecules across. Right? So it's a receptor, and normally the easiest way for it to not do any energy or work is if you have high concentration on one side and you're trying to get it to the side of the membrane and you let it go down its gradient, it enjoys it. It'll push, like there's a driving force to get it into that lower space. In cases where you have something built up already at high concentration in one area and you want to put more things into it, the system doesn't want to do it. But that's where you can use that phosphorylation from the ATP to do the work for you. So what's going to happen is, in a low concentration, when you're going toward low concentration, the push of refolding the protein is done literally because the molecule keeps hitting it and it's trying to get into this side to make itself fold into it. It refolds the protein and dumps out the other side, right? So the molecule's own energy is making it happen. In this case, the molecule's grabbed from the low concentration side. It doesn't want to go the other way. That's where the ATP comes in. It refolds the protein and it makes it do the switch from the energy from this guy, refolding the whole protein. That makes sense? At the same time, if you look at the mechanical work, this is one of my favorites. We're talking about those motor proteins carrying vesicles. So this, we're going all the way back to vesicle transport and how we get proteins from one compartment to the other one. You guys remember that? So in this case, this protein has a thing where it has the ability to bind. So let's say your feet would actually be able to grab, if I was the motor protein, they'd be able to actually recognize the microtubules, right? They can grab onto them. And then there's two parts where the ATP helps. It's like when they're walking, the motor proteins basically have knees. And it's kind of like when this one locks in, the ATP helps power up and refold it to make it stiff so it doesn't bend, and it makes it lean forward. And then it basically gives it enough to release this leg, and it kind of this floats around until it grabs on. Then the ATP refolds this one to make it stiff, and it makes the other one unlock, and it moves forward. So like literally your vesicle, as it's walking, every step you're burning ATP to make those feet grab on and keep moving forward, right? And it's, again, the ATP is that force that refolds that protein to make it grab, move forward, grab, move forward, grab, move forward. And then the coolest thing about ATP itself is that it's renewable. You can use it over and over again. So in this case, ATP, right, when you add water to it, you can break it up and you do the hydrolysis. Normally, when you have this broken ADP form in the phosphate groups, here you use your energy, right? Depending on what you are, for us is we eat our food, we take chemical energy from that, and we convert that. We normally charge domains, and that's what helps us glue these two things back together within a protein, gives us the ATP. Here, like I said, chemical reactions, movement of motor proteins, or transport of ions. This is where we basically can burn it off. So you can use the same thing over and over, the same ATP, use it, it cuts open, re-glue it back together in one domain like we make the food, and send it back out to your cells. All right. So talking about these reactions, trying to go from one step to the other one, right? There's going to be this set of proteins called enzymes that basically can help speed these things up, or they actually help move the reactions forward. So here, keywords, catalyst, right? So one of this, when you're talking about a catalyst, it's going to be a chemical that helps speed up the reaction, but it doesn't get used up within it, right? So for example, in here, when we're talking about this reaction, we go from ATP, it gets modified to become ADP and phosphate groups. The catalyst it itself doesn't change at all. So when it's done with the reaction, it should still be the same thing, right? And for us, what we're talking about today is going to be these proteins that serve this catalytic function. They'll help reactions move forward without themselves being used up. So let's say we had an imaginary one that was using the ATP, ADP to help the sugars go forward, right? We can imagine that it would grab the sugars, the ATP, it either helps bring them together, helps hold them in the right angle so they can glue them properly. Then you use the ATP to make them push them into each other, or it temporarily grabs onto one, holds the other one to help them glue together. And by doing that, it helps make it easier for them to actually come together. But then it can let go, and it's still that same exact protein. It can do it again to the next group, yeah? All right, so when we're talking about these reactions going forward, even though some of these reactions come like this, they can be exergenic, and you're going from a high energy state to a low energy state, you would think, hey, this should be progressing forward, it should be spontaneous, it should always happen, right? Here, this is a good example of actually burning something. And it's like, yeah, firewood, super high energy, right? When you're trying to make ash and you raise the fire, crazy amount of energy comes out in the form of light and heat, right? The problem is that this reaction, there's sometimes a little bit of this, which is called your energy of activation or activation energy, which is you need that little push to help it release the energy. For us, is you need a match, throw some gas on the fire, you light it up, a spark, to get that first block of energy to go over to make the reaction proceed forward. In this case, it's fire. Some of them, they're a little bit, the amount of energy that they need can vary, right? Some reactions, they're so sensitive that even the heat of this room could be enough to set it off. And then it can either ignite or something more explosive. But however much energy of activation you need to overcome that in order for the reaction to go forward. Otherwise, it's kind of held there. So here they're showing us with these three molecules, and you were looking at this imaginary molecules, and it was trying to glue B, trying to glue it with A, right? Even though the reaction should proceed forward in the sense of going, and it's exergetic, of going from a high energy to a low energy state, you'd expect that, hey, there's energy enough to the system to go forward. But because it has to do this little intermediate step where you literally need B and C to jiggle with each other, because they have a covalent bond, you need to break that and make it unstable enough so you can use its electrons and then grab onto the other partner. That jiggling force or that mechanical force of making this atom unstable, that's what you're basically going to be using for this part. Right? Part of that also too is like when these chemicals are going to like glue into each other. Let's say it will be Hank and Elsie will be the two chemicals. I'm the B particle, right? So first I'm matched up with Hank. We have our electrons flowing properly. We're sitting together. For my other, like, how the carbon has like 4 places where it can interact with, there's a certain arm here or a certain angle where this has to be so I can interact with Elsie, right? So if we're like fist bumping with Hank, we're hooked up, we have a covalent bond. Me and him have to be unstable enough to kind of push away from each other. At the same time, she has to be near enough so there's a chance that I can bump into her. But she's a free molecule. That means that she could be facing forward, she could be facing that way, she could be facing that way, she could be sideways like this. And that means her electrons to interact with me could be in a completely different spot. So even if I have enough energy to bump off of him, she might not be there to interact with me. Right? So all those things are going to make this reaction, like I have to bump off of him more and more times to have even a chance that I might accidentally bump into her at the right time to do the transfer over. So that means I need more and more energy to get this reaction to happen, right? And that's basically the energy of activation. All right. So here is where the enzymes can actually help lower this. And let's see where it goes. That's gonna bother me. Yeah, so they can help decrease this energy, right? And as an enzyme, you would imagine that it's a protein and it normally has a specific shape. Again, we're gonna go back to my rough example in the class. The protein, the way it could work is, if me and Hank, again, we're teamed up, right, we're covalently bonded, the enzyme can grab around us. And some of the things that it can do is, it could like grab Hank and basically twist him a little bit. So you can try bending the bonds. When it bends the bonds, it might make it harder for me and him to be fist bumping, right? So it makes it easier for me to fall off. The other thing is the enzymes could be doing is, they could be bringing her nearby, and maybe it's like, me and him will be bound, and she'll be right there, right? So it'll put her in the right place. So it's like, even if I do break once, I'm for sure going to be able to bond with her. Otherwise, if the thing wasn't there, I'd be bouncing off, but there's nobody there. There's less likely for it to happen. The other ones that they can do, one of my favorite ones is for the polymerase, the DNA polymerase. What it does is the enzyme, let's say it would be that big thing hugging us, it actually has a metal ion. And what it does is, I'm holding them with Hank, it temporarily lets me bind to the metal ion. It makes it easier for me to bind to the metal ion on that protein. That way it helps break the bond, and then it takes away the ion from me, and then it makes it easier for me to bind with her. But all of those are helping decrease this because it helps either decrease our interaction, the reactants interaction. It helps increase the interaction between, or the likelihood of the interaction between me and the product, or it gives me an intermediate to let me kind of bounce off of it to link up with the final product. Yeah? All right. So basically, that's where the protein can come in. It'll basically like hold the three of us. It'll push us, jiggle us around, so it can cause a shift to happen. But when it's done, it'll let go, and it'll find 3 new people, and it'll do the exact same thing. Or 3 new molecules, sorry. Oh my God, is that it? You guys have been so fast today. All right. I'm sorry, guys.
No worries.
Oh, yes.
So I feel like last night I was prepping this, I'm like, bro, I have to go fast, 'cause I have like only 15 minutes. But let me see. I did my drawings, yeah. Information. I showed my cool video. All right, so let's do a little quick review for your notes, right? So for cellular work, there's gonna be 3 different types. It should be chemical, transport, and mechanical. From those 3, the one I went into more detail about is gonna be that chemical, right? This is gonna be talking about this. The ATP going to ADP is gonna be a high energy to low energy, so it releases energy. We normally can use this release energy, again, on the chemical side, to make chemical reactions go forward, right? So we can use ATP to glue DNA, we can use ATP to glue proteins, we can use ATP to glue sugars together, yeah? Oh, this is the other drawing I had. This one I was missing. All right, so now if we look at the system as a whole, what's gonna happen is we're gonna be talking about, let's say, sucrose. Or basically, I kind of thinking of this from the side of, as an organism would be my food, right? So this is the high energy particle that I eat. Right? When I eat the sugar, this is basically gonna be the thing that's gonna help me bring in some energy. This will be the energy, right? And what I have cycling down here would be, if I had ADP, low energy molecule, and I have the phosphate group, right? And the goal is to get this into the high energy ATP state, right? If you're going from low energy to high energy, you have to have energy come in, right? And that's where my smooth fruit or my sugar, what I'm eating, is gonna be able to power this reaction up, and it's gonna drive that reaction. So in this case, right, at this level, this is an exergenic reaction. This was putting out energy, right? At this level here, for the ADP to ATP, this is endo, right? Because here we have a low energy, we're moving to high energy from that power. The next phase of this is, once your cell makes the ATP in the mitochondria, it can basically dump it up to the rest of your cell. So here we can go to any other organelle, any protein in the cytoplasm, protein on your plasma membrane, and the opposite is gonna happen, right? You're gonna have your ATP, it's gonna go to that spot. Here, whatever protein you want to fit into your story. So basically, it's gonna go back to being to this state, but the thing that's gonna dump out is those 7.3, yeah, your 7.3 into the whatever. So basically here, this is where you're dropping off your energy, right? At this dropping off the energy, on this side, we're expecting an enzyme reaction again, right? Because your ATP itself is dropping off energy. And what we're doing is, here, it can be the sugar, like you said, gluing two sugars together, changing this transport. Here you have an endo reaction that's gonna be powered forward, right? Something that shouldn't be happening normally, you have your ATP power up. So, you know, like those long stories that I like to put on midterms and stuff, right, about how your energy comes into the system. With an exothermic reaction, you can power up your ATPs. Once you've charged up ATPs, you can send them out to whatever transmembrane protein you want. At that transmembrane protein, they can drop off the energy. Right here is chemical, mechanical, or transport. They drop it off, changing an endothermic reaction so that it actually happens. Yeah? All right. And I think that's about it. If you guys have questions, we'll do some more questions, but other than that, Thanks, guys. Have a good weekend. Oh, homework. Still on Monday. What's up?
I was just gonna ask the thing you said about the midterm, were you just talking like simply about how like an endo, like these two reactions are like working together? Like in the same way this is working, it has to go one way and then it'll go back the other way and drop the energy pretty much?
Yeah, so this one. This reaction has to have more energy than this one.
Yeah.
And what's gonna happen is this will be that driving force of, like if we do the little piece. In this case, it'd be something like, going from this case to this case. The difference in this
Has to be greater than that.
has to be greater than the one that we're gonna have here. And that way we can transfer this energy to this, right? And same thing, the energy now that you're gonna have when your ATP, like this is gonna be your ATP. Your ATP now is gonna be the charged particle, right? And whatever you have with it, you're gonna charge that up, losing the energy from here. You're gonna use this energy to power up the next reaction to go from low to high. So this will be like the power ups, like this powers up this. Now that this is powered up, you can use the power from this one and transfer it to this thing. I'm almost thinking like those little battery packs, right? We used to charge your phone, or we used to have them today because our batteries were bad. We have a battery pack, you plug it into the wall, that would be here. You get power from your outlet, you charge up the battery pack. When you go out, you have your battery pack, you can use that to charge your cell phone. Right? But in the battery pack, you can bring it back, recharge it, and you can take it back out. When you go out. Yeah, yes.
It's just about the homework. Is it posted yet or is it gonna post later?
So about this later.
I mean, it's gonna be under like quizzes.
I think it always shows up under quizzes. Yeah. How does it normally look for you guys when I do the homework?
Normally goes for quizzes.
Quizzes, okay. I'll try to remember to do an announcement. Yeah. Thank you. Oh, thank you guys. Do they have your midterm? Yes, I'll give it to you right now.
Yeah.
Oh, don't forget homework. Talk to a professor. Talk about the research, and ask a question about the class, and then send me a hot paper, and we're good. Thanks, guys. Thank you.
I am going to.
No, we, tonight, right? Yeah, we're gonna. Yes.
Or one more, whatever we find out. I want to talk about this one. I have this one. All right, what's the matter like?
Oh,
10
yeah.
minutes, yeah, where are you? Okay.
This is a question, because why did you do that? Also,
Yeah, you can take it, so, I think you're up to just the class if you want to. And then, but it's best of both, that are pretty cool.
okay, thank you.
You gonna be in my class?
Yeah.
Yeah.
And is too, so.
Oh, dude, it's gonna be good.
Yeah.
Do you, I was just giving that to her. I also had a question on like courses. Do you think it's better to take 233 before 243?
Let's see, again, two, I still remember the number on that.
So I get them confused. I think 233 is like this class, like advanced, like genetics part 2, I think. Maybe 243 is genetics. I don't know, I just remember.
So I confuse them because I think 223 is genetics, 233 is molecular,
Oh, yeah.
and 243 is like another molecular thing.
Wait, hold on.
Yeah, let me open it up, I'm telling you that stuff, so. 233 is molecular. And 243 is molecular methods.
My guys are giving me this thing, I've like been trying to figure it out.
Yeah.
The one that you have in the lab is 243, right?
Yeah, 243.
Oh, okay, so does it matter? Like, cause next semester I probably have to take either this one or this one, so does it matter which one we take first?
I think you should be okay taking them concurrently. They're gonna, yeah, they're gonna be pretty much the same thing, kind of, like in this one, it's gonna be a little bit more like, I call them like almost like grad school, where we read a paper and we go super in depth into like the molecule RNA, how to work with it.
Oh,
Right.
okay.
And in this class, we're gonna be talking about kind of like almost here, like how the molecule sets up.
Yeah,
But we're gonna go into finer detail of like the spliceosome. We're actually gonna talk about it there heavily. Instead of you, I'm like, oh, there's a protein that cuts it up. I promise, right? There, we're gonna go heavy into it.
okay, and this one doesn't have the lab with it?
No, that one's just like, it'll be like this. Lecture
okay.
course. This one, it's like, to me, the best way I can describe this, to me, it's like what we had in grad school, where it's like,
Mhm.
we bring in papers and we talk about like, actually like the
Like
people have
research.
published, yeah.
Okay,
And then we're gonna do that kind of stuff in the lab.
okay, cool, thank you.